Hi there, Miss Barber here. This lesson is titled Graphs, Paths, and Circuits. We have some learning objectives for this lesson. First is to be able to demonstrate relationships in a graph. Second, be able to model relationships using graphs. And finally, the third learning objective is to be able to use the vocabulary of graph theory. We begin with some definitions. 1. A graph consists of a finite set of points called vertices. The singular form is vertex. And line segments or curves called edges that start and end at the vertices. An edge that starts and ends at the same vertex is called a loop. Locate each vertex on this graph. That includes the capital letters A, B, C, and D. Locate all of the edges. They are from A to B, A to D, A to C, B to C, B to D, and we also have one loop from C to C. Observe that where the edge AD and BC appear to cross, there is no point. Therefore, it is not a vertex. Example, understanding relationships in graphs. Explain why the figures below show equivalent graphs. Let's begin with figure A. It has vertices A, B, C, and D, and the edges that connect them are A to B, B to C, and C to D. Let's look at figure B. It also has vertices A, B, C, and D. It has edges that connects A to B, B to C, and C to D. Observe that these two graphs do not look similar. Even so, they are equivalent graphs because in both graphs, the vertices are A, B, C, and D. Furthermore, both graphs have an edge that connects vertex A to vertex B, an edge that connects vertex B to vertex C, and an edge that connects vertex C to vertex D. Example, modeling the Königsberg Bridge. In the early 1700s, the city of Königsberg, Germany was located on both banks and two islands of the Prego River. The figure below, image from slideshare.net, shows how the town's sections were connected by 7 bridges. Draw a graph that models the layout of Königsberg. Use vertices to represent the land masses and edges to represent the bridges. Let's label our drawing by first marking the north bank, and we'll call it N. Down below it will be our south bank, and we'll call that S. We have an island in the middle. We'll call the island C. Let's go ahead and denote that there's a river to the left, and then to the right of island C, we'll have island R for the right. Now, use vertices to represent the land masses. We'll use a dot to denote the north bank. We'll use a dot to denote the south bank, and we'll use a dot, the vertex, to denote the island C. Let's go ahead and use a dot to denote R, the right island. Now that we've got the vertices to represent the land masses, we will use edges to represent the bridges. We have one from north to the center. In fact, we have 2 bridges connecting the north bank to the center island. You have a bridge or an edge from the center to the south bank, and another bridge that'll take you back to the center. You have a bridge from the center island to the right island, You have a bridge from the north bank to the right island, and you also have a bridge from the south bank to the right island. Here is a graph that models the layout of Königsberg. Example, modeling bordering relationships for the New England states. A map of the New England states is given below. Draw a graph that models which New England states share a common border. Use vertices to represent the states and edges to represent common borders. Let's begin by using a vertex denoted ME to indicate Maine. The next state will use a dot and VT for Vermont. Between those two states, we'll use a vertex to denote New Hampshire with NH. Below New Hampshire, we'll use a vertex with MA to denote Massachusetts. To the left and a little bit lower from Massachusetts, we'll use a vertex and use CT to denote Connecticut, and we will use a dot to the right and below Massachusetts to denote Rhode Island, and we'll denote that RI. Now we have vertices that represent the states. We will draw edges to show common borders. You can get from Maine to New Hampshire, that's a common border. You can also get from New Hampshire to Vermont, and from Vermont to Massachusetts as well. There is a border between New Hampshire and Massachusetts. From Massachusetts, there's a border. You can go straight into Connecticut, as well as Rhode Island, and you can go from Connecticut to Rhode Island. Now we have edges representing the common borders. Circuits and paths will have some definitions. The second definition for this section, the degree of vertex is the number of edges at that vertex. 3. A vertex with an even number of edges attached to it is an even vertex. 4. A vertex with an odd number of edges attached to it is an odd vertex. Let's identify some degrees starting at vertex B. The degree is 2 as it has 2 edges attached to it. At vertex C, we see 3 edges attached to it. At vertex D, the degree is the number of edges attached to it, and that's 4. At vertex E, we count 1, 2, 3, 4, 5 edges, so the degree is 5. And now let's look at A. That degree is 4 because the loop contributes 2 degrees. Definition 5. 2 vertices in a graph are said to be adjacent if there is at least 1 edge connecting them. Example, identifying adjacent vertices. List the pairs of adjacent vertices for the given graph. We have a graph with vertices A, B, C, D, and E. There's an edge from A to D. There's an edge from B to C and B to D. There's an edge from C to D, D to E, and a loop at E. A systematic way to approach this problem is to first list all the pairs of adjacent vertices involving vertex A. Then all the vertices involving vertex B, but not A. And then vertex C, but neither A nor B for all the vertices. With this system in mind, The adjacent vertices are A and D, B and C, and B and D, C and D, D and E, and E and E. E and D because the loop connects vertex E to vertex E. Example, a map from Weather Underground Inc. below shows the states that make up part of the Midwestern states. The states are Michigan, Indiana, Ohio, Kentucky, and West Virginia. Part A. Construct a graph to show the states that share a common border. We'll begin by using a vertex for each of the states. We'll start with Michigan. We'll use a dot. Then we will write IN for Indiana. To the left and below Michigan, we'll denote that with a dot. Similarly, Ohio to the right of Indiana, we'll denote that with a dot. We also need to mark Kentucky. Below both Indiana, Ohio, and Michigan, we'll denote that with a dot. And West Virginia to the right of Kentucky, and we will denote that state with a dot. The dots are vertices and they represent the states. For the common borders, we use edges to connect them. You can get directly from Michigan to Indiana, as well as from Michigan to Ohio. You can travel directly from Indiana to Ohio. You can also travel directly from Indiana to Kentucky, and from Kentucky to Ohio, and Ohio to West Virginia, and finally Kentucky to West Virginia. The edges represent the common borders. B. Determine which states are even vertices. Even means an even number of edges coming from the vertex. The first one is Michigan. It has 2 edges coming from it. Ohio is also even. It has 4 edges coming out of it. And finally, we see that West Virginia is even as well. It has 2 edges coming out of that vertex. Part C. Determine which states are odd vertices. The first one I notice is Indiana. It has 3 edges coming out from its vertex. And finally, Kentucky. Kentucky also has 3 edges coming from its vertex. Another way to see this is that Kentucky borders these 3 states. Definition 6. A path in a graph is a sequence of adjacent vertices and the edges connecting them. Let's have an example of one. I'll let a path start at vertex A. We can traverse to B and then travel from B to vertex D. We can travel along the edge from D to F and then travel along the edge from F to E, and we'll let this path end at vertex E. The path is A, B, D, F, and E. Next definition. A circuit is a path that begins and ends at the same vertex. For variety, let's begin at C and travel to B. We will traverse along the edge from B to D, then D to F. We will go along the edge from F to E, and then from E back to C. This circuit starts and ends at the same vertex. Example, find a path and a circuit for the figure below. there are many paths and many circuits, we'll do one. Remembering that a path is any sequence of steps between adjacent vertices. An example, B to C to D to E. A circuit is any sequence of steps between adjacent vertices that begin and end at the same vertex. An example, B to C to D to E back to B, where it began. More definitions. A graph is said to be connected if for any two of its vertices there is at least one path connecting them. A graph that is not connected is called disconnected. Definition 10. A disconnected graph is made up of pieces that are connected by themselves, called components of the graph. Observe examples of connected graphs. Figure A. Notice a path can be drawn from any vertex of this graph to any other vertex of the graph. Same for figure B. Now let's look at disconnected graphs. In figure C, we see two separate components, namely the vertex C isolated and not connected to the parts of the graph A, B, and C that are connected. And figure D has two separate components, not connected. A bridge is an edge that, if removed from the connected graph, would create a disconnected graph. Example, list the bridges for the graphs below. Let's begin with figure A. The edge CA is a bridge. If that edge is removed, C would be standing alone, disconnected from the rest of the graph. Let's look at figure B. For figure B, its edge CA is a bridge, as well as edge DF.